Now we know what an arithmetic sequence is, we know what the terms look like in their general format, and we know how to calculate them. What we have to be able to do though, is if I give you an nth term, you have to be able to sum up all terms within the sequence to that point. So if I ask you what the sum of the first 100 terms of a sequence is, you have to be able to tell me what that is. Now this takes a very special format and is actually quite easy to use. So what we can do is we can determine the sum of an arithmetic sequence where terms take the format of the un equals a plus n minus 1 times d, that we already know, to any certain number of values using this formula here. Now that looks like an incredibly fun formula to use, but it actually was thought up by Carl Friedrich Gauss when he was 10 years old. When he was 10 years old, his teacher at the time had a habit of giving the class a very hard problem and a very long problem to keep them busy if they misbehaved in lessons. And what the teacher did was one day, Gauss was a wee bit naughty, and his teacher said to him to add up the first 100 whole numbers. He managed it within seconds using this formula. Now this formula is actually one that's not too difficult to prove and something you have to be able to do. Now in order to do that, let's imagine we look at the general format. So we know it's un equals a plus n minus 1 times d. Let's imagine that we were to write out that series in that sequence. So we know then that Sn, what we would get is we'd get a, the first term, plus a plus d, which would be the second term, plus a plus 2d, which would be my third term, plus my next term, which would be a plus 3d, and so on. And every term would take that format until we got to the very end, where we'd have our second last term of being a plus n minus 2d, and then the final term of the format, a plus n minus 1 times d. So that's how our sequence would look. Well, let's imagine we took that sequence and rewrote it again, this time though, writing it the other way round. So we'd start by writing the final term first this time. So we'd have a plus n minus 1 times d plus a plus n minus 2 times d, and then work our way all the way along again, right back to the start. What we then end up getting is we get our a plus 3d plus our a plus 2d, and then plus what would be the initial term, our u1, plus a. So we've got both of those there like that. If I then took these two series and these two sums and added them, what that would then give me is something of the format 2 Sn, so 2 times the sum up to the nth term, because I'm just going to go down and treat it like a column sum. That would then be 2a plus the n minus 1 d. If I added this term and this term together, so terms over each other, that would be like that. I would then add the a plus d to that one there, and what I'd then end up getting is plus 2a plus n minus 1 d. Look at that. We're starting to get the same term. And if I went all the way along each term, and again let's go to the final two terms and do the exact same thing, what I'd end up getting is that format for every single term the whole way along. So I'd then get plus 2a plus n minus 1d for my second last term, and then the final term, when I added the two of them up, I get 2a plus n minus 1 times d for that term. So they're all taking this same format, and I've got n of those terms. So what that would then mean is that 2 times the sum to the nth term would equal n times this set of terms. So it'd be n bracket 2a plus n minus 1 times d. So 2 times the sum would be this format. I want to know just what Sn, the sum, is. So if I divide it by 2, I'd then be able to say that Sn equals a half n bracket 2a plus n minus 1 times d. So this here was the formula that Gauss actually used to be able to add up that first 100 terms very quickly and easily. Safe to say he was a bright wee cookie at 10 years old. We can use this for any sequence that we want when we're working with looking at the limits, whether it's calculating them or using the limits of a function to determine other properties and other facts about them. So let's have a look at a few examples. Now imagine I want to find the sum of the first 10 terms of the arithmetic sequence which starts 2, 8, 14, etc. Now what we need to know is we first need to know what the nth term is. So I need to know what un equals a plus n minus 1 times d is. Now the key parts of that is I need to know what n is, so what term I'm going up to. So in this case I know that n is equal to 10. I need to know what a is, and I need to know what d is. If I know those three parts there, what I'm then able to do is then able to use the Sn equals a half n brackets 2a plus n minus 1 times d to be able to get the sum up to the nth term. So my a is just given by the first term, u1, which in this case is 2, and to get the common difference d, I just look at subtracting consecutive terms. So I do 8 take away 2, which gives me 6. I do 14 take away 8, which gives me 6. So I know my common difference d is equal to 6. Now for this one, it's the first 10 terms. So in this case, I also know that n is going to be equal to 10. So what I know for this sequence is that the sum of the first 10 terms is equal to a half times 10 bracket 2a, so 2 times 2, plus the n minus 1, so 10 minus 1, times the d, which in this case is 6. So that gives me a half times 10, so that gives me 5, bracket, 2 2s are 4, 10 take away 1 is 9, 9 6s are 54. So I then end up with 5 times 58, which in this case gives me 290. So there you go, that's the sum of the first 10 terms of the sequence, which takes this format as it goes up. So yeah, we can use it like that, and it's actually quite nice and straightforward to use. Slightly trickier one. So let's imagine I've got a sum of an arithmetic sequence that I want to calculate, and it looks this format, so 1, 7, 13, 19, great. I want to know though when it first exceeds 100. So I want to know when it first gets bigger than 100. So this is slightly trickier and slightly more intriguing to be able to answer. So in order to do this, what I have to do is I have to do the same thing as I did before. I have to be able to calculate my general format, so my general parts of it, so my a, my n, and my d. But the n is what we're after, so we're going to be using that throughout it. I then have to use the format of my sum and determine at which point that is bigger than 100. So again, our general format for any term would be un equals a plus n minus 1 times d. And I can equate it across to here. I know that u1 is equal to my a, which in this case is equal to 1. My d, which is the common difference, so I can get that if I do 7 take away 1, I get 6. 13 take away 7, I get 6. 19 take away 13, I get 6. So I know then that my common difference is 6. Now I don't know what term n is, so in this case, I don't have a value for n. So I'm going to keep it in my formula. Because I want to know the sum to which term gives me something greater than 100. So in this case, I've got a half times n, bracket 2a, so 2 times 1, plus my n minus 1, times d, which in this case is 6. So I've got a half times n, bracket 2, plus n minus 1 times 6, well let's multiply this bracket out, plus 6n, take away 6. So I've got a half n, 2 take away 6, so I've got 6n, take away 4, and I want to know at which point that is greater than 100. Well, this here, if I multiply this bracket out, it takes the form of a quadratic, so if I do that and get the 100 over, I want to know at which point this quadratic is bigger than 0, so I can solve it using that. So if I multiply this bracket out, I get 3n squared take away 2n. And if I shift the 100 over, I then have that take away 100 has to be bigger than 0. So I want to know at which point this is satisfied. So if I solve that, if I use the fact that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, so if I solve that using my quadratic formula, what I end up getting is two values for n. I'll end up getting that n is equal to 6.1 and n is equal to negative 5.4. Both of these to one decimal place, so I've rounded them to that. Now, I want to know at which point I'm going to be bigger than 100. Straight away, though, I can disregard one of these two answers. This one here tells me that my term is the 6.1th term, if you like. This one here tells me that my term is the negative 5.4th term. Well, you can't have that. I can't have a negative term, so it's that. So I know the solution that I'm looking at is n equals 6.1. But 6.1th term doesn't work. It has to be the next term after that. So in this case, what I can say is that n equals 7, so it's the 7th term. Now, looking at that, if you're thinking to yourself, great, if I rounded that though, if I rounded 6.1 to a whole number, I'd get 6. Well, 6.1 is greater than 6. If I was to use n equal to 6 and calculate the sum of the sequence for n equals 6, so let's actually go back to this here and substitute it in, I'd have a half times 6, bracket 6 times 6, take away 4. So I'd have a half times 6, which is 3, bracket 6, 6 are 36, take away 4, is 32, 3 32s are 96. So if I've rounded down, as it would suggest if you were thinking a normal rounding, I haven't hit 100 yet, so I've not exceeded it, so it's got to be the next term. Now I know that this kind of goes against the logic of rounding that we've known up to this point, where 0.1 would round down to 6, but at this stage we have to use a bit of logic. The previous term hasn't hit it, we know it's going to go after that, so that's why instead of rounding n equals 6.1 down to 6, we round up to 7. So at this stage of mathematics, when it comes into advanced higher, sometimes ignoring the rules that you've come across back in S1 and 2, when it comes to basic rounding, is something you have to do. Logic, thinking, all comes into it a bit more at this stage, and we have to be able to utilize that. So when we're looking at a question like this, always think to yourself, does it make sense? Does that answer what I want, what I have chosen? And then check it like we did here. So we now know the formula for the sum up to n terms of any arithmetic sequence. What we have to be able to do is utilize that formula in a variety of ways, including calculating the sum up to a set term, determining conditions like this one here, and even setting up systems of equations to determine A's and D's relating to set scenarios. So we have to be able to use it in a variety of ways, but we should hopefully be able to manage that.